So the periodic table here is color-coded in terms of whether or not the element's considered a metal, a non-metal, or a metalloid. So if it's considered a metal, the element has this background of sort of like a tan colored here. And if you notice, most of the elements on the periodic table are metals, and then you have the non-metals, and those are sort of color-coded based off of a sort of like a bluish color. Notice that hydrogen here is considered a non-metal, and so even though it's way over here, it sort of has properties of both metals and non-metals, and I've actually proven that hydrogen actually at certain temperatures and pressures does act and look like a metal. So it's kind of something interesting about hydrogen. Metalloids are in this sort of pink color, and here there are only 7 of them, and so they form sort of this stair step, and that's what sometimes for periodic tables that aren't color-coded, and of course your periodic table will not be color-coded for your tests, so it's important to be able to distinguish between metals, nonmetals, and metalloids. But sometimes periodic tables have like sort of like a step here, like drawn through, and the reason why we do that is because if you draw a diagonal line here, that's 5, starting with boron, that's 5 of your metalloids right there, and then you just have to remember that you have two additional elements there that are also metalloids, and so this sort of creates sort of like a divide here between the metals and the non-metals. Okay, and so your book will talk about differences between metals and non-metals and metalloids. They all have different physical and chemical properties. It's sort of like unique to their class of whether they're a metal or non-metal. But if you look at each individual element on the periodic table, you're going to have a lot of information by just looking at hydrogen, for example. They show you have the symbol here, capital H, for hydrogen, the element's name below that, and then below the symbol you have the atomic mass. Now, atomic mass is not a whole number for most of these elements, except the synthetically made ones, which are over here on the bottom. And that's because this is the average atomic mass. So it's the average atomic mass for all of the isotopes of hydrogen. And so most isotopes of hydrogen have atomic mass of 1, but some of them have atomic mass of 2, and some have atomic mass of 3. So this is an average atomic mass, and we'll talk later about how that's calculated. You can actually calculate the average atomic mass for each element if you knew how many isotopes there were for the element, and also their percent abundance. And then atomic number is basically telling you, atomic number tells you the number of protons or the number of electrons for a neutral atom. Okay, and then the difference between atomic mass for an isotope and atomic number is going to tell you the number of neutrons. And so if you don't know how to figure this out, I would suggest you do that. You know, there are a lot of different worksheets and that sort of thing online, if or you know, little Quizlets and stuff like that. You can go online and take a look, but being able to figure out how many protons, neutrons, and electrons there are for each element on the periodic table would be important. It's something that's sort of elementary that you probably did in high school, but sometimes it's important when we start to do some of the higher level things in chemistry. All right, so also this periodic table is color coded based off of whether the element is a solid, liquid, or gas at room temperature. And so if the letter is black, it is a solid at room temperature. If you notice, most of the letters here for the chemical symbols here are in black, so that means that, of course, they're solids. There are only 2 elements that are liquids at room temperature, mercury and bromine, and then the elements that have a red letter for the symbol are gases at room temperature, so hydrogen, all the noble gases, helium, neon, argon, krypton, xenon, radon. So all of these guys here are gases at room temperature. But notice most of the nonmetals are gases at room temperature. Most of the metals are solids at room temperature. and the metalloids are all solids at room temperature. So the next section, we're going to talk about measurements. Okay, so in the lab, we spend a lot of time doing measurements, and we have to know different properties and units that we use in the lab as scientists. Okay, it's a little bit different from what we use day to day living in the United States, for example. So in the United States, we use the English system, and as a scientist, we use the SI system, so we'll talk a little bit about that. So when we talk about measuring something, okay, you have to have some sort of value or number, okay? Then you also have to have a unit associated with that too. So, you know, when you're dealing with math, you know, it's all about numbers, but when you're dealing with chemistry or anything in science, you have to have a number and a unit. So it's not, the answer is not 5, it's 5 meters or 5 moles or some sort of unit that tells me not just the magnitude of the measurement, but also what are we talking about here? What are, you know, what is our standard of comparison for that measurement? Are we talking inches? Are we talking feet? Are we talking yards? You have to provide that information. So when you're writing out your answers, when you're doing calculations, make sure you include that value for the unit, okay, not just the number, but also the unit. It tells me a little bit about, you know, what that value is, what it represents. And when you're measuring something, you also have to have an indication of uncertainty of the measurement. Okay, so when we're using tools in the lab, there is a degree of uncertainty there. Okay, and I'll explain why in just a minute. So, as they point out, without units, a number doesn't mean anything in chemistry. Okay, and it's very confusing to me, especially if you just give me a number. I don't know what that number represents. So in chemistry, we use the SI system, or the International System of Units. It's been used since 1964, and so here you really need to familiarize yourself with the unit that we use, okay, for each different type of property that we're looking at. So for example, if we measure the length of one side of a cube, okay, the length is going to be in meters, okay, not in feet or inches. Okay, most of the time you probably have measured things with standard rulers. They're usually also marked not just with inches, but also in centimeters or millimeters. Okay, so that would also be appropriate to use if we're doing chemistry. We're going to use centimeters or millimeters and not inches or feet ever. Okay, so if we're dealing with mass, okay, rarely do we use the kilogram. A kilogram is 1,000 grams. That's a very large amount of substance, a kilogram. So normally in chemistry we use the gram. Okay, but you have to be familiar with properties and with the unit name and the symbol for the unit. Okay, time, we use seconds. Okay, that is the unit for time. For temperature, we use Kelvin. Okay, its symbol is a capital K. You're probably not used to using Kelvin when you're representing temperature. And so we'll learn later in the chapter how to convert from Celsius to Kelvin. And what you're familiar with, of course, the temperature units to be in Fahrenheit. And so we'll talk about how to convert from Fahrenheit to Celsius, and then how to convert from Celsius to Kelvin. Okay, and back and forth. If you've talked about, and we hardly ever talk about electric current, when we talk about electricity, we don't at all in this course. But the unit is the ampere, and its symbol is capital A. Amount of substances, the unit's a mole. We're going to talk about that a lot. The symbol for that is MOL. Luminous intensity is a candela. The symbol for that is CD. Alright, so sometimes we use prefixes, like you're probably used to centimeters and millimeters. And so here are the prefixes for the base unit when the unit is actually smaller than the base unit. So, for example, a decimeter is going to be a tenth of a meter. Okay, a centimeter is going to be 100th, and so on. A millimeter is going to be a 1,000th of a meter, and so on. So you see the factor that you're looking at. Here's the symbol. So a centimeter, the symbol for that is cm. A millimeter, mm. A micrometer. It's not an M. It looks like a U, and there's a Greek symbol there. Anyways, I'll show you on the board on Wednesday. So anyways, you have to be very familiar with the prefixes for the metric system. This is something that's not new. It shouldn't be new to you. You should have seen it in your high school science classes. I'm sure you have. If you're going the other way, if your value is greater than the base unit, so meters, for example, and then you have kilometers, right, or kilo, you have a symbol K there, so km would be kilometers, and so that's 1,000 times the length of a meter. A megameter would be 1 times 10 to the 6 times, so that's what, 1,000,000 times more than a meter, and so on. And so you need to look at these at the superscripts here and see how kilo is 10 to the 3rd, mega is 10 to the 6th, giga is 10 to the 9th, tera is 10 to the 12th. And you might be familiar with this if I think about a gigabyte or a terabyte in computer terms. You're probably familiar with that. And just anything you can use that already know from previous information, use that to harness the ability to memorize these things, because some of this stuff you should already know just by your daily knowledge of using computers. Alright, the SI unit of length is the meter. So here there are different definitions for the meter. So originally the meter was intended to be 1/10 millionth of a distance from the North Pole to the equator, and now it's defined as the distance the light travels in a vacuum in 1 over 299,792,458 of 1 second. So a meteor is 3 inches longer than a yard. So if you've probably looked at a meter stick. So here's the length of a meter stick in comparison versus a yard, and so there's 3 inches difference. A centimeter is very small. If you look at a standard ruler, of course you have inches on one side and then centimeters on the other, right? An inch is equal to 2.54 centimeters. Okay, a meter is a little bit longer than a yard, right? 3 inches longer than a yard, and it's equal to 39.36 inches. And so here's just a figure showing you the length of a meter versus the length of a yard, or centimeters versus inches, and so on. And because I'm sure most of you have used rulers throughout your academic career as a high school and middle school student, I'm sure that you're very familiar with the length of a meter and approximately how long a meter is, roughly. So for mass, the SI unit for mass is the kilogram. So it's defined as a mass of a liter. It was originally defined as a mass of a liter of water. So a liter of water is 1,000 milliliters, and so that's each milliliter is 1 gram, so it's 1,000 grams. 1,000 grams is 1 kilogram. So now it's defined by a certain cylinder of platinum, iridium alloy, which is kept in France. Okay, so it's 1 kilogram is about 2.2 pounds, and here's a picture of a replica, a prototype of a kilogram, and so the mass of that metal cylinder there is roughly 1 kilogram. All right, so what about temperature? We said the base unit for temperature for the SI system is the Kelvin. Okay, notice that Kelvin, we do not say Kelvin degrees. Okay, and you don't see the symbol there either for degrees. And the reason for that is because the Kelvin scale is an absolute scale, meaning that temperature of 0 Kelvin is theoretically